Okay, so for our last video on cost-benefit analysis, we're going to talk about how you deal with uncertainties in the calculations. As you've seen from the case studies already, that we'd make our best effort in calculating the measures where we can, but there may be cases where we're uncertain about the true value of a parameter we estimated or one that we just had to simply guess for. So in circumstances like that, what we can do is something called a break-even analysis to identify the value a parameter must take in order for your expected net benefit to be zero. So if you're trying to decide which parameter to vary, pick the one that you're most uncertain about. So this can often be P0, the probability of an attack without a security investment. So let's see what happens. Well, before you sort of think that this is a real problem for cybersecurity, that we have all this uncertainty, this may be some consolation, is that we're not alone. Many disciplines have this problem of estimating the probability of a rare event occurring. And so this quote here I quite like. It came from a National Academy study looking at bioterrorism risks. And what they said is the assessment of probabilities that adversaries will choose courses of action should be the outputs of analysis, not required input parameters. So what this is basically saying is that we should turn this question on its head, and rather than think about how we can come up with better ways to estimate things like the probability of attack, we should estimate the things that we can, and then produce the probability of attack that's required for our defense to be cost effective instead. So we can do that. So we go back to our expected net benefit calculations, with the risk reduction factor in there. All we need to do is set the n-bis to 0 and then solve for the variable that we're interested in varying. So in this case, it could be P0. So we rearrange the equation, and we end up with the break-even probability P0 simply being the cost of the security countermeasure divided by the risk reduction times the loss amount. And so then once we have that, we just try a range of parameter values to see what the break-even probability of attack should be. So for you, what you should do is go back to case 1, our example of bridges, and retrofitting bridges against attacks, and fill in this equation here. So what is the break-even probability for an attack occurring? Once you're done, carry on. All right, so it turns out to be this, 260K divided by 0.9 times our various loss calculations. What that means is that the break-even probability needs to be 0.002, so a 2 in 1,000 chance that a bridge is going to collapse in a given year. Which might sound low, but it's actually extremely high, given that we have hundreds of thousands of bridges that could potentially need protecting. And so what you can do with this is that let's say you're even somewhat uncertain about the other costs as well. You can come up with a graph, or in this case a two-dimensional table, which is done in the paper on bridges. Where we look here on the rows are the costs of your security measures, and then on the right we have in the columns the losses from successful terrorist attacks, range from $10 billion all the way up to $100 billion, which is a lot. And we can see what the break-even probability needs to be. So it really varies quite wildly, right? So if your countermeasure is cheap and it only costs you $1,000 and the expected loss is, say, $1 billion, well, that's 0.0001. But if your losses are somewhat, say, low, like maybe in the $100 million range, and it costs you, say, $100 million to take the defensive countermeasures, well, that would mean that you need to have 105 attacks on that one resource per year in order for it to be cost effective, which is clearly not in the cards. So what you need for this particular case is a very low probability in order to make this cost effective. So tables like this can really guide decision makers in figuring out whether or not it's really worth making the investment. Now for case 2, with the wastewater treatment, where we can similarly solve for this. If we just first fill in the things that we actually had a very good estimate for, which was the overall expected loss, the cost, and the rate reduction, where there was a bit more uncertainty on. So we can actually then plot in R how we want to vary what the cost and the risk reduction is. And so that's what we have. So what's plotted here is the break-even P0 value for an increasing risk reduction probability. And we have 3 lines for 3 different cost bases. And so again, this is a nice graph which sort of communicates visually what a decision maker should consider. So P0 is one possibility for an output of our cost-benefit analysis, but another common variable that you'd want to consider is the risk reduction factor. So you might know what the a priori probability of an attack is from looking at historical data, for instance, but maybe you're uncertain about the effectiveness of your countermeasure. And so in that case, we'll solve, take your NBIS, set it to 0, and solve for R. And we end up with an equation like this, which is cost divided by P0 times lambda, which is so basically our cost divided by our expected loss with the lack of security. And then from there, we can see the range of parameter values that would make the break-even risk reduction acceptable. And here's another plot for that. And you can see that it varies in this case by the configuration that a given city has, in terms of the number of sewer miles it has, and then that can then lead to, for however much your system costs, how much risk reduction you need to actually get from your system. And anytime the risk reduction is, say, between 0.9 to 1, then that's starting to become infeasible. Anything above 1.0 is by definition infeasible. And so that tells you a cost that you can never exceed and still justify investment. Now, we're going to stop the video here, but on the slides we have code for this particular slide, and we also have a couple of examples that we're going to work through in class. So thank you for your attention.